Welcome everyone. I'm Ramya from 3rd B.Sc Chemistry, studying in Koveri College for Women, Tiruchirappalli. In this session, let us discuss about Ellingham diagram. In this topic, let us see about thermodynamic principles of metallurgy, Ellingham diagram, formation of metal oxides, and observations of Ellingham diagram. From thermodynamics, we know that delta G naught equal to delta H naught minus T delta S naught, where delta G naught is the Gibbs free energy, delta H naught is the enthalpy, and delta S naught is the entropy. And this equation is similar to the straight line equation, that is y equal to mx plus c. So, if you plot delta G naught along y-axis and T along x-axis, you will get delta H naught as intercept and minus delta S naught as a slope. This graph is called Ellingham diagram. Ellingham diagram is a graphical representation of variation of the standard Gibbs free energy of the reaction for the formation of various metal oxides with the temperature is called Ellingham diagram. Let us consider the formation of metal oxide as an equilibrium reaction. Then, if the standard Gibbs free energy change is negative, then the reaction is spontaneous and the metal oxide is considered to be stable. In the other hand, if the standard Gibbs free energy change is positive, the reaction becomes non-spontaneous and the metal oxide is considered as unstable. Standard Gibbs free energy change can be calculated from the famous thermodynamic expression, that is delta G naught minus RT ln Kp, where Kp is the equilibrium constant in terms of partial pressure, which is given by partial pressure of a metal oxide divided by partial pressure of metal into partial pressure of oxygen, and this can be simplified since the partial pressure of a solid are taken as unity, so it is equal to 1 divided by partial pressure of oxygen. So we can write delta G naught, which is equal to minus RT ln 1 divided by partial pressure of oxygen. For the Ellingham diagram, you should write the formation of metal oxide reaction for 1 mole of the oxygen. In the graph, we can see that 4 molecules of aluminium combines with 3 molecules of oxygen. So we need to divide the whole equation by 3. And if you see the graph, there is a certain change in the slope for some lines. For example, if you see the line for a mercury oxide, at a particular point, the slope of a line changes because at that point it reaches its boiling point. A solid mercury oxide suddenly becomes a gas. So, there is a phase transition, and in the case of magnesium oxide also, at a particular point it reaches its melting point. So, solid magnesium oxide suddenly becomes liquid due to the phase transition. The slope changes. Then, the observations of Ellingham diagram. For a metal oxide, the slope is always positive. The slope is negative for carbon monoxide. As the temperature increases, delta G becomes less negative and becomes 0 at particular temperature. At a higher temperature, metal oxide possesses less stability and easier decomposition. Due to the phase transition, there will be a sudden change in the slope at a particular temperature for the metal oxide, as we had already discussed that magnesium oxide and aluminium oxide. That's all for the today's session. Thank you everyone. Have a nice day.